So here is a general overview of today's talk. So I will build a connection between information elicitation and information aggregation by addressing two corresponding problems. One is a mechanism design problem, another is a learning problem, simultaneously through the same information theoretical approach. So basically, I will distill the essence of these two problems to the design of proper information measurements. And after we get the proper information measurements, we can apply this information theory thing to address the problems immediately. OK, so now let's start to talk about the two corresponding problems. So the first one is a mechanism design problem. Another one is a learning problem. OK, so we want to forecast whether a step will succeed or not. So what we can do is we can elicit the forecast from the crowds. And we want to incentivize them to tell the truth. So here, tell the truth means that for each agent, Alice, she has some private information which is relevant to this step. And we want her to report her Bayesian update conditioning on her private information. And one typical solution in this scenario is we can just use proper scoring rule to incentivize them to tell the truth. But the problem is, if we use proper scoring rule, and then we can only pay them only after the outcome is revealed. And if we want to pay them immediately, and still we want to incentivize them to tell the truth without knowing the outcome. And this problem is actually very relevant to a literature called peer prediction. So like in peer prediction, the main difference is that in peer prediction, we also want to incentivize people to tell the truth without any verification, without knowing ground truth. But in most literature, peer prediction literature, like agents, they actually report discrete signals like yes or no. And here, we want agents to report forecast. And this problem is actually proposed by Witkowski and et al. In 2017. And they achieve the same property with proper scoring rule, but only with mild verification. So they only require the knowledge of the unbiased estimator of the optimal forecast. And then we can see actually this forecast elicitation without verification, this problem is not fully solved. Like I mentioned before, in the peer prediction, people usually report discrete signal, not forecast. And in Witkowski et al., in that paper, they still require mild verification. And in addition to this problem, another question we want to ask is that in the traditional setting, we only ask the crowds to forecast one step. And if we have two steps, very similar step, and if we have these two forecasting tasks, can we do better? So here, we do better means that can we design the mechanism that can achieve better properties? And it turns out the answer is yes. So without any verification, with additional assumptions, conditional independence assumption, which I will talk in detail later, we can design the mechanism in the single forecasting task setting. Like we can make, like, if you believe everyone else tell the truth, then you will have strict incentive to tell the truth as well. And in the multi-task setting, like if we have, like, even it's only two multiple tasks, we can achieve a much better property, which we call strongly truthful. So we not only can make truth-telling being a strict equilibrium, but also it is best, like it pays better than any other strategy profiles, and it pays strictly better than any other less informative strategy profile. So here I omit the formal definition here, but you can think of the permutation strategy profile as some like unnatural, risky thing. So it is already a very strong property. And now let's explain why we need this conditional independence assumption. So we need that for each agent Alice, we need to find a reference agent Bob for her such that Alice and Bob's information are conditional independent, conditioning on the result we want to forecast. So the reason we want is, like, let's consider a extreme case. Like if Alice and Bob, they always have the same private information, In this case, that contradicts the conditional independent assumption. And here, it's impossible to achieve the strongly truthful property because they can always pretend they have the full knowledge of the event they want to forecast by claiming that y equals the first bit of their private information. And in this case, no other strategy, like no mechanism can make truth telling be better than this kind of simple occlusion. And also, we need this assumption because we want to avoid paying the bias. Like assuming like if both Alice and Bob, the forecast the outcome of the startup only based on the gender of the CEO. In this case, it's impossible to avoid paying them this bias information. So in some sense, this conditional independent assumption is necessary. And actually, it turns out the property we achieve is the ultimate property in both of the settings. Okay, so now let's introduce another problem. It's a learning problem. And we will see like this problem is actually the same problem with the mechanism design problem. Okay, so it's in our learning setting, and we still want to forecast whether the startup will succeed or not. So here is the learning, so we do not have the forecast from the crowds. Actually, we have the features. So we have two views of this startup. One view is the feature of the startup, like the target customer, the funding, the information about the CEO. Another view is the cross-source feedback. And we have two predictors. You can also think as two hypotheses. So the predictor PA takes the feature as input and outputs the probability the forecast the startup will succeed or not. And the predictor PB, it takes the cross-source feedback as the input and also outputs the probability the startup will succeed or not. And we can think the first predictor as some neural network, and we can think the second predictor as some weighted average. And the typical assumption in co-training is like conditioning on the information we are interested in, we want to forecast. The two views of the data, they are independent with each other. So it can be understood as that the thing we are interested in is actually the intersection of the two views. And the problem we want to solve in co-training setting is that how can we evaluate the performance of the two predictors? And second is how can we train the predictors if we have a bunch of predictor candidates? And without considering time complexity, this is essentially the same problem. Because if you know how to evaluate the predictor, and then you can just pick the best pair of predictors that has the highest evaluation. And this evaluation problem is not hard if we are in the supervised learning setting. Like for example, if we have 3 data points, each data point is about a startup, and we have a predictor PA and takes the feature as the input and outputs the forecast. And if we have a reliable label, which is the outcome of the startup, and then it's very easy for us to tell whether this predictor did a good job or bad job. Actually, for this example here, the predictor here actually did a very good job. And we can use any loss function we want to use. We can, for example, we can just use the proper scoring rule. But it's not a trivial question in the co-training setting, because in the co-training setting, we are only given 2 unreliable predictors. And in this case, it's a little bit hard to tell whether they did a good job or not. And this problem is proposed by Blum and Mitchell in 1998. And their motivation is they want to aggregate 2 views of data, and they want to train the 2 predictors, 2 hypotheses simultaneously. And the gap in this literature is that most co-training work, they only deal with hard hypothesis. So hard means that it takes the feature as input, but only output a discrete signal. And soft means non-hard. And also, like, they usually assume the hypothesis space, like the predictor candidates, is already weakly good. And moreover, they lack a unified and rigorous approach to the general setting. And we propose a family of optimization goals, and such that the predictor we want is actually the maximizer of our optimization goal. And also, we show a new connection between the mechanism, the information elicitation, and information aggregation. And we leave the sample complexity analysis as an open question. To talk about the connection, let's compare with the previous work. So in 2017 and 2018, Liu and Chen, they proposed a very interesting work. They used some clever learning techniques to help design the mechanisms, peer prediction style mechanisms. So they show that learning can help peer prediction. And in 2015, Igor and Igor, they have very different setup. They show the connection between a supervised learning problem and a property elicitation problem. And in contrast, we show that peer prediction helps unsupervised learning. And moreover, we not only show the connection between the elicitation and aggregation, we also show the connection between them and the information measurement. Okay. So now let's start to talk about the challenge of these two problems and also why these two problems are equivalent. Okay. So for the forecast elicitation problem, one naive idea can be like if both Alice and Bob, they tell the truth, and then their predictions should be similar with each other because they are forecasting the same thing. And in this case, can we pay for agreement? And this naive idea turns out work for the if we only want to prove the strictly truthful, which means that if we only want to prove truth-telling is a strict equilibrium, but we need to pick the agreement measurement carefully, and I omit the detail here. But this will not work if we want to achieve a much better property called strongly truthful, which means that if we want truth-telling being the best strategy profile. So why? Because if we only pay people according to the number of agreements, and then what they can do is they can just ignore their information, their private information, and always report 100% succeed, 0% fail. In this case, they do not report any useful information, but they can achieve the maximum amount of agreements and also the maximum amount of payment. And it turns out in the co-training setting, we have the same problem. Remember that we want to evaluate whether the pair of predictors did a good job or not. And intuitively, we can just pay for the agreement between the two predictors. We can, if we have a bunch of data points, we can just insert the two views of the data point into the two predictors separately, and then compare whether they agree with each other every round. And this idea will work if we can assume like when the predictor is already weakly good. And then we can use that weakly good predictor to boost another predictor, and then we can do this interaction. But the problem is without this assumption, it will not work. And it's the same reason. Because if we only if our optimization goal is maximizing the agreements between the two predictors, and then the best pair of predictor will be meaningless. Because the best pair of predictors, they will ignore the input and will always output the same useless information. And we can see these two problems has the same challenge premise. Okay. Okay. So and also they are the same problem because the key observation is that human beings actually can be thought as machine, and the strategy of human being can be also thought as the hypothesis placed by the machine. And how to evaluate the predictor is equivalent as how to pay them to incentivize them to tell the truth, and how to train the predictor. We just pick the predictor that has a highest evaluation. Is this like including the 3 minutes I borrow from my next talk?
Yes.
Oh, okay. Oh no, okay. Okay, now let's talk about the solution quickly. So I'm going to borrow the techniques in peer predictions. And that is a mechanism design framework we designed before, and the building block is mutual information measurement. So basically, it is a family of information measures, and it measures the correlation between two random variables is always non-negative. If they are independent with each other, is 0, so very intuitive. And the good thing is it satisfies a property called information monotonicity. So if Alice's original information is X, Bob's original information is Y, and then when they apply any strategy on their information, the mutual information is going to become smaller. So this is a visualization of this information monotonicity. And now we can just pay Alice and Bob an unbiased estimator of this F mutual information. And information monotonicity will imply strongly truthful. Recall that strongly truthful says that truth telling is the best strategy profile. And if we pay them this mutual information, and if they apply other strategies, they will lose information. They're going to be paid smaller. But the hard part is how can we construct the unbiased estimator in this case? And that is actually the main technical novelty of this paper. And the idea is we not only pay them for the number of agreements, we also we calibrate by minus the number of expected agreements. And the number, so like there are 3 data points here, and the number of agreements means that we can just randomly pick a startup and to calculate the dot product between their forecasts. And for the expected agreements, we just pick a pair of startups which is not the same startup, like startup 1, startup 2, and we also calculate the agreements. This is the expected agreements. And it turns out that all agreements, they have higher agreements there, but they also have higher expected agreements because for every line, they just report the same thing. And in this case, they cannot do well here. And it turns out this property can make the Alice and Bob's payment is always bounded by the F mutual information between their private information. And the maximum is obtained if they tell the truth. And recall that the code training is actually the same thing. So let me skip this part here. So basically, in the mechanism development part, we just pay them this formula I mentioned before. And in the code training part, what we do is we just pick the pair of predictors that maximize this F mutual information gain. And by the same proof, we can show that the best predictor is a predictor that doing this Bayesian posterior thing. OK, and now we propose this family of information theory optimization goal. And we also propose this new connection between the information elicitation, information aggregation, information measurements. So remember that when they tell the truth or when they do the best, we can actually calculate the F mutual information. So it also provides, so when we do this information aggregation thing, it also provides a way to measure the information. So that is why I see these 3 things are very correlated with each other. So here is a summary. So in this talk, I build a connection between elicitation and aggregation by propose the 2 corresponding problems, turns out to be the same problem, and show that they have the same challenge as our agreement challenge, and we can solve them by the same information theoretical approach. Okay. And the future work will be, for the learning part, one is just run the experiment. And also, we want to analyze the sample complexity, the Bayesian error. Another interesting thing is the influence of the choice of convex function f. So in our result, we do not care. We only care if as long as f is convex. But when we consider to analyze the convergence traits, I think the choice of f will be important. And also, we want to apply it in the feature selection. And in the mechanism design part, in addition to the experiment thing, we also want to explore more about how to estimate the information structure. Means that we do not need any private information to know that who is Alice's reference agent, whose information is conditional independent with Alice. Okay. Thanks.
Any questions from the audience before the second talk? Actually, I have a question. I have a question about so how does this learning depends on the choice of your convex regularizer, like in practice when you actually apply this different.
I tried a little bit numerical experiment there, and I realized that the choice of f, like the convexity of f, will influence the convergence rate. So they will have the same maximum, but when they go to the maximum, the convexity of f is actually affect the rate you go to that maximum.
I see. And is the steepness like somehow, like does the steepness experimentally somehow like seem to improve like the convergence rate, or?
I just try a little bit for this. So
okay.
yeah.
Any other questions?
Just ask a quick question. So why permutation strategy is still equilibrium? So why?
Oh. So permutation strategy here means that like if I think 80% probability succeed, 20% probability fail, then I'll always flip it. I always see 20% probability succeed and 80%. And in this case, like if both Alice and Bob do this thing, without any prior knowledge, we cannot distinguish the true thing and this permutation. So that is why.